In the vast cosmic theatre, gravity is the undisputed star of the show. It's the silent, unseen force that choreographs the dance of planets, stars, and entire galaxies. For over a century, our understanding of this basic force has been shaped by Albert Einstein's theory of general relativity. It describes gravity not as a force, but as a curve in the fabric of space-time itself, caused by mass and energy. This elegant picture has passed every test we've thrown at it, from the bending of starlight to gravitational waves. However, deep in the heart of physics, there's a tempting and persistent whisper. What if there's more to the story? What if gravity is connected to another basic property of the universe that we often take for granted? Temperature? This is the bold question asked by a speculative but fascinating idea known as the Thermal-Gravitational Expansion Theory, or TGET. The theory suggests a big break from classic and relativistic physics. It suggests that the gravitational pull a body has might not just depend on its mass, but also on its heat. In this view, a cold object and a hot object, even if they have the exact same mass, might have slightly different gravitational pulls. This isn't just a small tweak to our current models, it's a potential revolution. It means there's a hidden link between the big world of thermodynamics, the science of heat and temperature, and the cosmic world of gravity. Two areas of physics that have historically been treated as almost completely separate. Imagine two identical cannonballs side by side. From everything we know, their gravitational pull is the same. But what if we froze one close to absolute zero and heated the other to a scorching temperature? TGET suggests that their gravitational fields would be different, even if only a little. The implications are amazing. This could mean that the gravitational constant, G, which we've long thought of as a universal and unchanging value, might have a subtle dependence on the heat energy of the masses interacting. This would force us to re-examine everything, from the precise orbits of satellites to the evolution of stars and the formation of the large structures of the cosmos. It would be like discovering a new basic rule in the cosmic game that we thought we had figured out. The idea might sound like science fiction, but it comes from the deep cracks in our current understanding of the universe. Physics is still struggling with mysteries like dark matter and dark energy, which together make up 95% of the cosmos. These puzzles tell us that our picture is incomplete. Maybe the solution isn't just a new particle or a new field, but a new property of the forces we already know. Exploring the possibility that gravity is sensitive to temperature is a bold leap into this unknown territory. It's a quest to see if a familiar force has been hiding a secret from us all this time, a secret that could reveal a deeper, more unified description of reality. To chase such a groundbreaking idea, you need an experiment that's just as ambitious. That's the whole point of the CryoTAD Project, a bold science effort made to hear the tiniest whisper of gravity that depends on temperature. The mission's name, short for Cryogenic Torsion Balance for Anomalous Drag, hints at how it works. But its goal is special and deep. To find a super tiny, almost invisible difference in the pull of gravity from objects at very different temperatures. The challenge is huge, pushing what we can do with technology to its very edge. The force CryoTAD wants to measure is unbelievably small, like femtonewtons. That's 10 to the power of minus 15 newtons. To give you an idea, 1 femtonewton is about the same as the gravity pull one single human red blood cell has on another one a few feet away. It's a force so weak, it's a trillion times weaker than the force you use to press one key on a keyboard. Measuring such a delicate whisper from the universe is like trying to hear a pin drop in the middle of a rock concert. Every possible source of disturbance, the shaking from a passing truck, the hum of the lab's air conditioning, even the tiny ground tremors from Earth itself, can easily drown out the signal. The scientific reason, though, is strong enough to make this huge effort worth it. If CryoTAD found this weird force, it would be one of the biggest discoveries ever in physics. It would be the first real proof that our idea of gravity is not complete, and that TGET, or something like it, holds part of the truth. It would open a new window into how reality truly works, suggesting a deeper connection between the rules for really big things, gravity, and the rules for really tiny things, quantum mechanics and thermodynamics. Such a discovery wouldn't just win a Nobel Prize. It would rewrite textbooks and set the path for a new age of physics, both in ideas and experiments. It would make us rethink the very basics of how we understand the universe. The project is then a high-stakes, high-reward adventure. It's a trip into unknown territory, guided by a map of guesses. The scientists and engineers behind CryoTAD are like modern-day explorers, building a ship to sail through a sea of uncertainty. They're not just testing a theory. They're looking into what physical laws really are. They're asking the universe a direct question. Is there more to gravity than just mass? The difficulty of this task shows how well Einstein's theory has worked for us. But the very fact that this experiment exists shows our endless curiosity and our refusal to believe we know everything. How do you build a machine sensitive enough to measure a force that's almost nothing? The design of the CryoTAD experiment is a masterclass in precision engineering, a delicate dance of cooling, isolation, and measurement. At its heart is an instrument known as a torsion balance, a device with a long and famous history in measuring weak forces. Imagine a dumbbell hanging from its middle by a very thin, delicate fiber. If a force pulls on one of the masses, the dumbbell will twist, turning the fiber. By measuring the angle of this tiny twist, we can figure out how strong the force is. CryoTAD uses an incredibly refined next-generation version of this classic design. The entire setup is placed inside a cryostat, which is like a fancy high-tech thermos designed to bring the core of the experiment to amazingly low temperatures. The target temperature is just 4 Kelvin, which is like minus 269 degrees Celsius or minus 452 degrees Fahrenheit. This is only a few degrees above absolute zero, the coldest temperature possible in theory, where all atomic movement almost stops. This extreme cold serves two really important purposes. First, it's super important for the main goal of the experiment, to create a huge temperature difference between the test masses. Second, it greatly cuts down on thermal noise, which is the random jiggling of atoms. Without this, those tiny movements would create vibrations that would completely mess up the delicate measurement. The main parts of the experiment are the masses themselves. These aren't just random pieces of metal, they are carefully made cylinders of tungsten, a material chosen because it's super dense. More density means more mass packed into a smaller space, which makes the gravity signal as strong as possible. The experiment uses a set of these tungsten masses. Some are kept at the base cold temperature of 4 K, while others are heated up from time to time. The torsion balance, which also works in this super cold environment, is designed to measure the gravity pull between these hot and cold masses. The whole system is amazing because it's layered with insulation, designed to block out the noisy outside world and only listen for the tiny gravity conversation happening inside. To spot the tiny twist of the torsion balance, the experiment doesn't use human eyes or a simple microscope. Instead, it uses a super-sensitive method called optical interferometry. A laser beam is split, with one part bouncing off a mirror on the torsion balance and the other serving as a reference. When these two beams come back together, they create a pattern of light and dark lines. Even the smallest twist of the balance causes a change in this pattern, which can be measured with incredible accuracy. This lets researchers find rotation angles much smaller than any mechanical sensor could ever achieve, turning a whisper of force into a measurable light signal. The CryoTAD experiment is like a carefully planned dance happening in the quiet, super cold world of 4 Kelvin. The main players are the tungsten masses, a set of fixed source masses, and the test masses attached to the super-sensitive torsion balance. The source masses are the ones whose temperature is actively controlled. In a typical cycle, these masses are heated up every so often from the starting point of 4 Kelvin to a higher temperature, maybe around 40 Kelvin. This creates the important temperature difference that TGET says should change the gravitational force. This heating isn't done with a simple flame. It's done with very precise heaters that can slowly and carefully raise the temperature without causing shaking or other problems. This regular heating and cooling process is called temperature modulation. Think of it like flipping a switch on and off at a very specific beat. If TGET is right, then as the source masses heat up, their gravitational pull on the torsion balance should change a little bit. As they cool down again, the force should go back to normal. This on and off cycle creates a rhythmic swinging signal. The torsion balance should swing back and forth perfectly in time with the temperature changes of the source masses. This modulation is the key to telling a real signal from random noise. A constant, strange force could be caused by some unknown problem in the setup, but a force that appears and disappears perfectly in time with the heating cycle is solid proof. The whole setup is made for this rhythmic measurement. the source masses are placed on a spinning platform that slowly turns around the torsion balance. This allows the experiment to look at the gravitational pull from different angles and helps get rid of any regular errors that might come from imperfections in the shape or density of the masses. The mix of temperature changes and physical spinning creates a complex but very specific signal pattern. The challenge for the scientists is to build a detector and analysis system that are perfectly tuned to hear this very specific song. A gravitational hum that goes up and down with temperature, spinning as the masses rotate. The process is super slow. A single measurement cycle can take hours or even days to finish, as the masses are gently heated and allowed to cool, while the direction of the torsion balance is constantly watched. Thousands of these cycles are repeated for months, allowing researchers to average the results and build up enough data to be sure. It's a search that needs huge patience. Every piece of data is a valuable clue gathered from the very edge of what can be measured. The experiment shows how slow, careful, and detailed cutting-edge science is, where a big discovery might be hidden in years of careful, repeated, and super precise observations. In an experiment as delicate as CryoTAD, the signal is the hero of the story, but the villain is noise. Noise is any unwanted disturbance that can mimic or hide the signal you're trying to find. Beating this villain is, without a doubt, the hardest part of the whole project. The team has to create a super quiet environment, both mechanically and thermally. The first line of defense is a multi-layered vibration isolation system. The entire cryostat, which weighs several tons, sits on a fancy platform that uses springs and shock absorbers to keep it safe from ground vibrations, letting the experiment float, untouched by the Earth's rumbling. Inside the cryostat, the fight against noise keeps going. The extreme cold of 4 Kelvin is a strong friend, as it gets rid of many sources of heat noise. At room temperature, atoms are always moving randomly, creating a background shake that would mess up the measurement. By cooling the whole torsion balance and its immediate area to almost absolute zero, this atomic shaking is brought down to a minimum. But the experiment itself needs a temperature difference, since some masses get hot. This creates a new problem, making sure this heat doesn't get out and cause unwanted thermal expansion or radiation pressure that could push the torsion balance and create a false signal. To handle this, the experiment uses fancy thermal shielding. Imagine a bunch of shiny nested radiation shields, like the layers of a Russian doll, placed between the hot source masses and the cold torsion balance. These shields, also cooled to super cold temperatures, catch stray heat radiation, stopping it from reaching the sensitive detector. Also, heating and cooling the source masses must be done with extreme care. The system is made to make sure the temperature difference is steady and precisely known, without causing any gas to escape or mechanical stress that could create false forces. It's a tricky balancing act, creating a temperature difference while keeping perfect thermal and mechanical isolation. Even with all these precautions, some noise will always be there. This is where smart experiment design comes in. Signal modulation, both changing the temperature and rotating the source masses, is a powerful tool for getting rid of noise. Most noise sources are random or have a different frequency. For example, a random vibration might cause a quick movement, but it won't be in sync with the exact frequency of the temperature cycle. By using clever data analysis to look for only a signal that matches this specific preset rhythm, scientists can filter out most of the background noise. Basically, they're telling their computer, ignore everything you hear unless it has this exact beat. At the heart of any scientific theory is an equation, a short and sweet math sentence that tells you its main idea. For the Thermal-Gravitational Expansion Theory, or TGT, the main idea can be put into a surprisingly simple change to Newton's law of gravity. The proposed equation for the force between two masses, m1 and m2, separated by a distance r, looks like this: F equals minus g sub 0 times 1 plus alpha times the sum of t1 and t2 times m1 times m2 divided by r squared. Let's break this down. The first part, minus g sub 0 times m1 m2 over r squared, is super familiar. It's Newton's classic law of universal gravitation. G sub 0 is the gravitational constant as we know it, measured at or near absolute zero temperature. The minus sign just tells us that gravity pulls things together. The groundbreaking part is the new term in the middle, 1 plus alpha times the sum of T1 and T2. Here, T1 and T2 stand for the temperatures of the two masses. and alpha, which is the Greek letter, is the crucial new ingredient. The alpha parameter is called the thermal-gravitational coupling coefficient. It's a new basic constant of nature proposed by TGET, and it tells us how strongly temperature affects gravity. If alpha is exactly 0, the alpha times T1 plus T2 part disappears, and the equation goes back to Newton's familiar law. In this case, temperature has no effect on gravity, and TGT is wrong. However, if alpha has a small but positive value, it means that as temperatures T1 or T2 go up, the overall gravitational force gets a tiny bit stronger. The whole point of the CryoTAD experiment is to measure the value of alpha. Finding a non-zero value for alpha would be, honestly, the discovery of a lifetime. This equation gives us a clear prediction that we can test. By setting up a system where we control the masses, the distance, and the temperatures, we can look for a force that acts exactly as this formula says it should. The CryoTAD experiment is designed to do just that. It fixes the masses and distance, and then systematically changes one of the temperatures, T1, while keeping the other, T2, steady at 4 Kelvin. Then it looks for a tiny change in the force, F, that is directly related to the temperature change. If such a change is found, its size would let scientists figure out the value of alpha for the very first time. The beauty of this equation is how simple it is and how big its impact could be. It doesn't throw out centuries of physics, it builds on them by adding just one new term. This term, however, opens up a whole new world of possibilities. It suggests a deep connection between the shape of space-time and the way heat works in tiny particles. The search for alpha is therefore more than just a measurement. It's a hunt for a number that could tell us if our understanding of one of the universe's most basic forces has been missing a key piece of the puzzle all along. It might just be the key to unlocking a new and more complete theory of physics. Collecting petabytes of data from the CryoTAD experiment is only half the battle. The real challenge is finding the super tiny signal buried within a mountain of instrument noise. This is where the power of modern data analysis, machine learning, and clever computer programs really come in handy. The main tool used is a technique called a lock-in amplifier, which can be built into hardware or used as a software program. A lock-in amplifier is made specifically to pull out a signal with a known frequency from a very noisy environment. It works by multiplying the raw experimental data by a reference signal that has the exact same frequency as the expected gravity change, that is, the frequency of the temperature change. Think of it like this. Imagine you're in a crowded room where everyone is talking at once. If you're trying to listen to a friend who is sending a message with a specific rhythmic pattern, you could focus your attention by mentally filtering out that rhythm. A lock-in algorithm does this mathematically. By multiplying the noisy data stream by the clean reference rhythm, signals that are in sync, or match the rhythm, get stronger, while all the random noise which is out of sync tends to average out to 0 over time. This technique allows the CryoTAD team to greatly increase how sensitive they are and pull a clear signal from the noise, revealing a whisper that would otherwise be completely unheard. To make the signal even clearer, the analysis often uses other advanced filters. One powerful tool is the Kalman filter, a program widely used in guidance systems for airplanes and spacecraft. A Kalman filter is really good at predicting what a system will do next, based on what it's doing now, and a model of how it should behave. In CryoTAD, it can be used to model how the torsion balance moves, predicting its motion based on known physics and filtering out random changes that don't fit the model. This helps to smooth out the data and reduce the effect of sudden, unpredictable noise spikes, giving a clearer view of the underlying physical process. In recent years, artificial intelligence and machine learning have also become powerful helpers in this search. AI programs can be trained with fake data that includes a known TGET signal mixed with realistic noise, to learn how to recognize the subtle signs of the temperature-dependent force. The trained AI can then be used on the real experiment data to look for similar patterns that might be too complicated or too faint for traditional programs to find. This many-sided approach, combining old-school signal processing with new AI, creates a powerful set of digital tools, a kind of ghost in the machine that can see through the noise and give a verdict on one of physics' most exciting questions. After years of building, calibrating, and collecting data, the CryoTAD experiment will eventually reach its moment of truth. The final outcome will lead humanity to one of two doors: each opening to a dramatically different future for fundamental physics. The first door is one of groundbreaking discovery. This is the scenario where the analysis reveals a clear, statistically significant non-zero signal, matching the predictions of the Thermal-Gravitational Expansion Theory. The team would detect a tiny, oscillating force on the torsion balance, perfectly in sync with the heating and cooling of the source masses. This would be undeniable proof that gravity is in fact temperature-dependent. The consequences of walking through this door would be huge for the scientific community. It would signal the beginning of a new era in physics. General relativity, while still a brilliant approximation, would be shown to be incomplete. A new fundamental constant of nature, alpha, would be added to our textbooks. Theoretical physicists worldwide would rush to develop a deeper theory to explain why temperature affects gravity, potentially leading to breakthroughs in quantum gravity and our understanding of dark energy. It would be a paradigm shift like we haven't seen since Einstein's time, a discovery that would reshape our cosmic story and open up completely new avenues of research and technological possibilities. The second door represents what some might call failure, but in science, it's more accurately described as a null result. This is the scenario where, after all the analysis, no signal is found. The data shows that, up to the unprecedented sensitivity of the CryoTAD experiment, there is no detectable influence of temperature on gravity. The value of alpha would be limited to 0, or at least an incredibly small new upper bound. While this might seem less exciting, it is an equally profound and important scientific outcome. It wouldn't be a failure of the experiment, but a triumph of its precision. A null result would provide the strongest evidence to date that gravitational interaction depends purely on mass and energy, just as Einstein predicted. It would set the tightest limits ever seen for TGT and any other alternative theories of gravity that propose a link to thermodynamics. This would effectively close this particular line of research, allowing scientists to focus their efforts on other promising avenues in the search for new physics. It would strengthen the foundation of general relativity, telling us that, whatever the solutions to the universe's big mysteries are, they probably don't lie in a temperature-dependent G. A null result strengthens our current theories by showing how rigorously they've been tested and have survived. The story of CryoTAD is more than just a tale of tungsten, cryostats and lasers. It's a perfect example of the spirit of scientific research. It shows our natural and strong human desire to understand the universe as deeply as possible. It starts with a simple, almost childlike question. What if? What if one of nature's most basic forces had a quality we'd never noticed before? This question, born from curiosity and imagination, kicks off a chain of events that pushes the limits of technology and what we all know. It inspires physicists and engineers to design and build machines that are, by any reasonable measure, impossible. This journey reminds us that science isn't a fixed collection of facts, but a lively and ongoing process of asking questions. The theories we believe today, like general relativity, are the best descriptions of reality we have, but they aren't sacred texts. They are maps, and like all maps, they might have blank spots or mistakes. The only way to find out is to go into unknown territory with experiments like CryoTAD. These projects are our ships of discovery, sailing to explore the edges of the known world. They are driven by the understanding that even our most cherished theories must be constantly tested and challenged. Whether CryoTAD finds a new force or confirms what we already understand, its legacy is secure. The new technologies made for the project, in cryogenics, in precise measuring, in noise blocking, and in data analysis, will be used in other areas of science and technology. The experiment will train a new group of scientists, giving them the skills and courage to tackle the next big cosmic mysteries. It serves as a strong reminder that progress is made by those who are willing to ask bold questions and seek the answers with care and persistence, no matter how hard the path is. In the end, our cosmic journey is a never-ending cycle of wonder, questioning, testing, and discovery. We look at the night sky and don't just see dots of light. We see a huge puzzle waiting to be solved. Experiments like CryoTAD are our attempt to find another piece of that puzzle. It's an example of our species' most noble quality, our endless curiosity. We are how the universe knows itself. And as long as we keep asking questions and building the tools to find the answers, our space-time adventure will continue, leading us to a deeper and richer understanding of the cosmos we are lucky enough to call home.